Okay, so we're continuing this series on the channel capacity theorem, and what I wanted to talk about first was signal levels. Okay, so for our 4PAM system, we're using 4 signal levels. We could have used just 2 signal levels, okay, where we, for example, might have used a 1 and a -1. Okay, but if you use a 1 and a -1, that gives you a certain power level. Okay, in our 4PAM system, we used 3, 1, -1, -3. And you can see that these aren't really comparable in the sense that the power for this first signal is going to be much less than if I sent signals that included also 3s, 1s, -1s, and -3s. Okay, so what we really need to do is figure out what would the signal levels be for a given power constraint. Okay, and so one way to think about that is to consider signal levels that are spaced apart by a distance d. Okay, so let me get rid of this. And let's say we had 2 levels, and this is spaced apart by d. All right, then if we were going to come up with the power of this, this would be d over 2 minus d over 2 squared plus d over 2 and squared. And you would be able to calculate the power associated with using just 2 levels. All right? And if we normalize that to say, for example, 1, if we set power equal to 1 and use that as a constraint, we could solve this equation for d, and we would get d is square root 2. All right? Well, what if I add more levels? Okay, so if I had 4 levels, all right, and these are spaced apart by d, then the power constraint that I would be looking at would be this level, which is minus 3d over 2, minus d over 2, d over 2, 3d over 2, and we just square all those. All right, so you could collapse this down into, using symmetry, multiply by 2, d over 2 squared plus 3d over 2 squared. And we can normalize that, set that equal to 1, okay, and solve for d. And if you do that, you would get d is equal to 0.4472. All right, so I can do that in general, and I wrote a quick MATLAB script to show you the distance between signal levels for a given power constraint. So we see when there are 2 symbols, I know that says k equal 1, so add 1 to all these values. This is for n equal 2, this is for n equal 4, this is for n equal 8. Okay, so we see the number of signal levels moving up as powers of 2, and each time the distance between the symbol levels drops fairly dramatically. Okay, all right, so let's think about that. Our 4PAM system, we're used to looking at soft decision diagrams, and we've seen things that look like, here's a 1, here's a 3, -1, -3. And so we start to send symbols through the channel, and we pick up received values, and we can plot those, and it makes this nice soft decision diagram if there's no noise. Everything falls right on the levels. But what happens if there's noise? Okay, then we start getting values that are hopefully close to the symbol values. There starts to be some spread. We've seen this before. Okay, and if there's too much noise, then of course what starts to happen is you start to transmit, you're transmitting a -1 and you might get something up here which would get decoded as a 1, which generates an error. Right? So you see there's this trade-off between constrained power and noise level. So as the noise level gets too large, then what you're going to have happen is there's going to be lots of cases where the received signal value moves up out of the decision zone. Okay, so if I transmit a -1, I need everything to land in here. Okay, because if it lands out here, it gets moved to a -3. All right, so hopefully you can see that as we add signal levels, yes, we can increase the bit rate of the communication system. Okay, so for example, if we had 8 levels, now we're sending 3 bits per transmission, or per message, or per pulse, however you want to call it. But the number of levels increasing means the distance between the symbols is having to decrease, and that makes us more susceptible to a given level of noise. All right, so I think that covers this. We've talked about signal levels, we talked about a power constraint, and that if you have too much noise, you start to close the eye diagram or make it where there's not distinctions between the signal levels once you send the symbols through the communication system. Okay, so off to the next step on the channel capacity theorem.